Hello, students, and welcome back for our second lecture of this week regarding alcohols. And in the beginning, in the first lecture, we talked about how to name alcohols. We also talked about various reactions that we've seen before that can produce alcohols, and some new ones that involve the reduction of carbonyls to produce alcohols. Now we're going to start by talking about some other reactions of alcohols. We'll start with talking about how we can prepare diols. So again, we've seen some other reactions in the past that we've used to produce diols. We're going to see some of those reactions again and some different ones. So let's get started here. Diols, in terms of nomenclature, we haven't named diols yet. So it's relatively simple. If you have two alcohol groups, instead of ending the name with ol, you're going to end it with diol. And what's going to come before that will be a little bit different too. So here we have an example. In this example, we have 1, 2, 3 carbons. And so we're going to say propane for the 3 carbons, but there's alcohol groups on each end, and so we're going to say diol. So diol for 2 alcohol groups, and propane for the fact that they're attached to a propane primary chain. And then we use locants to indicate where the alcohol is. So this is carbon number 1, number 2, number 3. And so we're going to say 1, 3 propane diol here. Okay. Here's another example of a diol to the right here. And here we have a carbon chain that has 6 carbons. And here we have different positions of the alcohol. This one's a terminal alcohol right here all the way on the last carbon. This one's on the second carbon. So that's going to influence the way we write our locants. We're going to start the locants so that we start with the alcohol that's right at the end. So we have an alcohol on carbon number 1. We're going to go 2, 3, 4, 5, and 6. So since the primary chain has 6 carbons, that's called hexane, and it has 2 alcohol groups attached to it. It's going to be called hexane diol. And those alcohol groups are on carbon number 1 and carbon number 5. So this would be called 1,5-hexane diol. And here, this one, down here, this one would technically be called ethane diol, but unfortunately it has a common name that's very, very common. Everyone calls this ethylene glycol. Ethylene glycol is probably what's in the radiator of your automobile. It's a solution of ethylene glycol, or propylene glycol sometimes, which is the same, but it just has one other carbon like this. That would be propylene glycol. These are antifreeze. They raise the boiling point and reduce the freezing point of water when dissolved in them by boiling point elevation and freezing point depression. Hopefully you learned about that in general chemistry, Chem 150. But glycol is often used as a common name to talk about compounds with 2 hydroxyl groups as well. So diols can be formed from the reduction of molecules that have 2 carbonyls, and we've seen molecules that have 2 carbonyls before too when we did ozonolysis, right? And so synthetically, if you're making a diol when the alcohols are far apart from one another, one synthetic path might be to have a alkene of some kind. Like in this case, we would, if we had a double bond here, and then each of these had this, and it was 1, 2, 3, 4, 5. If we had this and we did ozone, and then the ozonolysis, then we could we could then produce this guy right here, right? We would chop, basically. We would chop right here. I think I'm missing a reagent here, but I'll just say ozonolysis. And we could produce this, and then if we could go on to do a reduction, and we could use H2 and palladium. Remember that this is a strong reducing agent, so this would also reduce an alkene, these are milder reducing agents, so these would not reduce the alkenes if we had them. In this case, we don't really care because we don't have an alkene, so we can use any one of these, but the reduction will give us 2 alcohols. Remember, adding hydrogens, reductions, right? So adding hydrogen here and here, uh, and so that leads to this reduction. So we can make diols from the reduction of diketones or dicarbonyls of some kind. We also, if we're making neighboring hydroxyl groups here, we've had ways to do that in the past. We had a treatment with a hydroperoxide here, followed up by acid to produce anti-dihydroxylation. We learned about that in chapter 8. And also catalytic dihydrogenation with the osmium O4, which would produce the syn dihydroxylation. And so either of those reactions can also produce diols. These diols would be on neighboring carbons. Finally, we're going to learn about a very valuable synthetic reaction in this chapter, and it's called the Grignard reaction. So this one is very valuable synthetically because in the past we only had one way to increase the number of carbon atoms in our molecule, and that was through the use of a alkylnide ion. If you remember alkylnide, we would produce an alkylnide ion from a terminal alkyne like this, and then that would be a nucleophile. And so if this reacted with, for example, an alkyl halide, this could produce for us a larger hydrocarbon chain. Now, we're going to have a new way to produce a larger hydrocarbon chain, and that's going to be the Grignard reaction. And the Grignard reaction is more useful because magnesium's cheap. Magnesium is a very cheap, abundant metal, and we don't need to make an alkyne, which generally involves a lot more reactions of producing an alkyne because you just don't have those lying around. And so if we start with some type of alkyl halide, we can react it with magnesium, and effectively what that does is it puts the magnesium atom in between the carbon atom and the halogen atom. So for example, here, if we have this bromobenzene and we react with magnesium, we can put the magnesium right between the carbon atom on the benzene and the bromine atom. Or if we have this chloropropane, we can react with magnesium and put a magnesium right between the carbon atom and the chlorine atom. Now, what's this going to do for us? Well, first of all, we got a name for it. When you make this, when you react the magnesium with the alkyl halide, and you get that magnesium between the carbon and the halogen atom, we call that a Grignard reagent. And the Grignard reagent has some valuable properties to it for us. Basically, it makes for us a carbanion. So we needed a carbanion to act as a nucleophile so that it could do a nucleophilic substitution and increase the carbon chain. Now we're going to have a new way of making a carbanion. It's this Grignard. Because the carbon atom actually has a significantly greater electronegativity than the magnesium, this results in a polar bond here between the magnesium and the carbon. In fact, it's so polar, it's more like an ion. So it's like we've already got the carbanion, but it's a little bit stabilized by the fact that it's attracted to this magnesium, so they're kind of almost bonded. But we've got this carbanion. And like the carbanion with the alkylnide ion, what we have to be careful of is that we don't have it, we can't have any protic solvent. That's very important. If we have anything that could provide a proton, remember, this is going to be super basic. Even more basic than the alkylnide ion. So any hint of water or methanol or ethanol, any kind of protic solvent is going to, anything slightly, even slightly acidic is going to protonate this. So one of the great challenges of doing a Grignard reaction, which you will do next semester, is in fact trying to make sure everything stays dry, because any water will protonate this and will destroy your Grignard reagent. But this is a way that we can make a carbanion that can then be a nucleophile and then do the same types of substitutions we had with the alkylnide ions. It will also be, of course, a super strong base as well. So we're just going to call now the Grignard reagent, we're going to call it R-. Okay? It could be anything. It could be any carbanion, but it's a carbanion, it's negative, and it's going to attack a carbonyl. So we reacted with a carbonyl. Remember, the carbonyl here too is polar too. It's partially negative on the oxygen. It's partially positive where the carbon is. So that's carbanion is going to want to attack right there where the carbon is. So we have the nucleophilic attack on the carbonyl. And at that point, we have this resonance arrow, just like we had when we had the hydride ion, which was also a nucleophile. It would attack here. We had this resonance arrow to put the negative charge up on the oxygen to make sure we're not showing a carbon with 5 bonds. That just doesn't happen. And then we'll follow it up afterwards. So after the Grignard reagent has been used up, it's no longer there anymore, right? So now in a separate, as a workup step, meaning in a separate flask afterwards, we're now, or after this reaction is over with, then we're going to add a protic, something like an acid, and that will provide the proton. So then we'll have a proton transfer, and then we'll protonate it, and then we get the alcohol. So what the Grignard gives you is it gives you a molecule that ends up as an alcohol, and it also ends up with more carbon atoms. Whatever you had here in the Grignard, whatever carbon atoms you had, those are now a part of your molecule. And so in terms of synthesis, what you're going to want to be looking for is when you've got something with more carbon atoms and is also an alcohol, that's a dead giveaway. Grignard happened. Okay. And so, again, as I said, you got to be very careful when you do this. Practically speaking, when we do it in the lab next semester, we're going to have to be very, very careful that all of our glassware is extremely dry, because any little bit of water is going to protonate our Grignard, which is super basic, and then it will not work anymore. So we're going to have to be very careful. What we're going to do is we're going to take our glassware, we're going to put it in the oven beforehand to make sure all the water is evaporated, and then we're going to take everything and we're going to seal it up, protect it from the water in the atmosphere, so that it can react, because the water is so much more acidic than an alkane is. So it will protonate this. This will only go one direction here, this way, and then you will no longer have your Grignard. We need this so it can react with our carbonyl and produce this alcohol with more carbon atoms than our carbonyl had. And so we don't want to expose it to water, because that will destroy our Grignard reagent. And so in terms of solvent, it will usually be like an ether. Anhydrous, meaning no water in it, dry ether. So here's a couple of examples of Grignard reactions. So again, the dead giveaway is you have an alcohol with more carbon atoms than what you started with, right? So here we're starting with 6 carbon atoms. We got the Grignard. Remember, this is the carbanion. So effectively, it's going to be the CH3 minus, like this, right? And that's going to go, and that's going to attack right in there. And then this goes up, and we get this oxide ion, but then we work it up with water or something protic, and that will protonate it. And that's the proton right here that came from the water. And so we have the alcohol, and we have one more carbon atom. Started with 6, now we have 7. Right? So now another one here, same thing. This group here, this is the carbanion. It's going to attack. It's a CH3 minus. And it's going to attack right there. Okay. And then, of course, this will go up, and then it'll get protonated by the water. So this water right here, this is going to be this proton, and then this methyl group is now attached. So again, we've got one more carbon atom, and we have an alcohol. Important reminder, the carbonyl is trigonal planar. So this attack can come from equal opportunity from front or back. And so it's important to note that we're going to, if we have a chiral carbon, this carbon wasn't chiral, but this one is. If we have a chiral carbon, we're going to get a racemic mixture of products here. And so it's going to be important for you to note that, either by indicating that it's racemic like this, or drawing an enantiomer and saying plus En. When it comes to esters here, remember the mechanism. You don't want to try to memorize what the products will be. You want to remember the mechanism. Okay? And when this happens, this is going to happen twice, just like we saw with the hydride ions, because let me, yeah. So what we're going to have is we're going to have the nucleophilic attack. This guy's going to go here. Okay. And then we're going to get this. I'm going to continue it here on the side. And if you understand this mechanism, then you don't have to memorize what's going to happen, right? Which is hard. And then we're going to have, remember that this is going to, usually these alkoxides are terrible leaving groups. However, whoops, I have a double bond here. This should be single. Oh no, I erased the whole thing. Oh no, I went to the next slide. There it is. Eraser. All right. And so, alrighty. So this is a single bond, right? Because we move these electrons up here. But now we're going to have the loss of this leaving group. This leaves, and now what we've got is we've got a carbonyl again. This time it's, we have one hydrogen here. It's an aldehyde. I can draw the hydrogen in. The hydrogen was there. It just wasn't drawn in. And now we have still the other, we have more of the Grignard reagent here. And so this can attack again. Whoops, and my, I forgot my methyl group. Oh my God, sorry guys. Okay, let me go through this again because that was kind of bad explanation. So we have the attack by the methyl group, and the resonance arrow puts the electrons here. So that methyl group is now there. And there's no hydrogen, sorry guys. Okay, it's the methyl group. Because we had a double bond here. Yeah, sorry. Let me explain that again. So no hydrogen here, no hydrogen. I got ahead of myself there. This methyl group attacks, right? There's just these three bonds. One to this carbon, one to this oxygen, two to this oxygen. So that's double bond here, two single bonds. 3 atoms bonded, no hydrogens. The methyl group attacks. The resonance arrow here puts the negative charge up here on the oxygen. And now we have the methyl group attached. So the methyl group is now attached. So I'm going to draw it in. Boom, right there. The methoxy group leaves. So we have the loss of the leaving group. This methyl group is still here. It's not a hydrogen. It's this methyl group. This one right here is this one right here. But now we still have a carbonyl. So we have another nucleophilic attack by the second bit here of the Grignard reagent, and now the protonation can happen. We have this oxide ion. We still have this methyl group, but now we have another methyl group, this one right here. Okay, and now we just treat with water. So that's this next step, water. We put water in there, and we get the protonation. Boom, boom. And then finally we have our final product, which is the alcohol and then the 2 methyl groups. And that's this one right here. So we added 2 methyl groups. So when you have an ester, just like with the hydride ion, we can add 2 hydrides. With the ester, we can add 2 methyl groups by the Grignard. And so it's just a nucleophilic attack, right? It's actually the only thing that's new is the fact that is the way that we're making the nucleophile. But other than that, it's just this SN2, right? Really pretty simple. But as long as you understand the mechanism, this mechanism, I love to ask about this mechanism on the final. I guarantee you, I will ask you 100% about a Grignard mechanism on the final. 100%. Okay. It's super important to understand because it's going to come back to in Chem 213 and be important again. Okay. In terms of the Grignard, now what if we're trying to do a Grignard on a molecule that already has an alcohol? Now that is a problem. If you don't understand why it's a problem, I want you to stop this video and look back at the previous slides and think about why it's a problem. Why is it a problem to have an alcohol group on a molecule that you're trying to make a Grignard. It's going to mess up the Grignard. How? Think about it. Stop. Okay, hopefully you figured it out. This Grignard can't be formed. Why? Because if we make this Grignard, then what we've got is essentially what we've got is this OH, and we've got a carbanion here, and we've got the magnesium. Sure, we got the magnesium, we got the bromine over here, but we have the carbanion here, and we have an acidic alcohol. What's going to happen? This proton, there's going to be a proton transfer. The proton transfer is going to go like this. Whoop. And then this in this bond, it's going to go like that. And then the proton's going to go over here, and then we'll have an alkoxide ion. It's not going to work. Okay. So if we want to get this Grignard product here, we're going to have to do something else. We're going to have to make it so this proton cannot be transferred over here to our Grignard. So what we're going to do is we're going to do what's called protecting the alcohol. Okay. So we're going to protect the alcohol. That way the proton can't come off. And then we're going to do the Grignard reaction. And then we're going to deprotonate it. That's going to be the idea. So let's look at this in a little bit more detail. In terms of what will we protect it with, we're going to replace the proton. And we're going to replace the proton with a trimethylsilyl group. Trimethyl, 3 methyls, and silicon, silyl. Trimethylsilyl. And we can call this for short OTMS. Okay. So we're going to react this with chlorotrimethylsilane. And we're going to do this in an amine aprotic type solvent. Okay. Triethylamine. And so that's going to replace the hydrogen here with this TMS group, this trimethylsilyl group. And we'll get the triethyl amino ion, trimethyl ammonium ion, and chloride. It's going to take the proton, it's going to put it on the nitrogen. So the point of the nitrogen is to grab the proton. It's a base. Now, the substitution here that occurs for the silicon atom, it occurs by a nucleophilic attack on the silicon atom. The oxygen does a nucleophilic attack on the silicon atom, and then the chlorine leaves. Now, you may be thinking, how does this happen? There's 3 methyl groups. This silicon is sterically hindered, right? Well, it's a silicon and not a carbon. That's the big difference. If you had a trimethyl methane, or whatever, that wouldn't be the right word. It would be a terbutyl chloride. If you had a terbutyl chloride, the carbon atom's so small, the oxygen could not attack the carbon atom. However, with silicon, it's a bigger atom, so the oxygen can more easily get in there and attack the silicon. And so that's the way it works here. So essentially, it's like a SN2. So this is SN2-like when it attaches to the silicon here. But it can do that even with the trimethylsilane, because the silicon atom is a lot bigger than a carbon atom. So after that, we're going to have to find a way to remove it. And so the way we remove it is with an acid, basically. At that point, we're just putting a proton back on, and the trimethylsilyl group leaves. Or we can also use fluoride ions. The fluoride ions will essentially do the same thing. And so the source of the fluoride ions is often tetrabutyl ammonium fluoride here. So this is tetrabutyl, 4 butyls, ammonium ion. It's a positive formal charge because the nitrogen's making 4 bonds. And then that's the cation, and the anion is fluoride. So what's this going to look like? How are you going to write this in terms of if you're writing a synthesis? If you have a alcohol that you want to make a Grignard reagent, you're going to start by protecting the alcohol. So you use trimethylsilyl chloride and triethylamine, and that will protect it. And then you write it as OTMS. The hydrogen comes off, and the trimethylsilyl group is on. Then you just do your normal Grignard reaction. So we do a Grignard magnesium. We react with a carbonyl here. Any carbonyl, there could be anything on there. And so when it reacts with the carbonyl, now we'll have the Grignard here will attack right in here. And so you'll get the alcohol group that comes from this right here. So that this here becomes the alcohol group. These two R groups, whatever they are, hydrogen or whatever, they're going to be there. And then this whole part right here, this is going to be attached. And we're going to still have the OTMS, so we'll use the tetrabutyl ammonium fluoride to deprotect it. And then we get the final product. And so we can turn a molecule that has an alcohol into a Grignard reagent. Okay, but we need to protect the alcohol first and then remove it at the end. So that's a Grignard. And so now we have two ways to add carbon atoms. Okay, in one way, you won't necessarily get an alcohol, okay, as a product. It's using the alkylnide ion with the carbon-carbon triple bond deprotonated by the amide ion. Or we can use the Grignard. And one extra step is if the Grignard has an OH, we have to protect the OH before we finish that. Okay, let's move on to talking about phenols a little bit. So phenol, very, very commonly industrial produced as well. It's produced from benzene. Benzene comes from fossil fuels, the same place as your gasoline. First, it's reacted with phosphoric acid and with propene. Propene also comes from fossil fuels. So these both are from fossil fuels, and we use the phosphoric acid to catalyze this. We get the we get the isopropyl benzene here. At that point, we react with oxygen. We oxidize it to produce a peroxide. Peroxide is easily produced here because it's benzyl. It's a benzyl peroxide. So remember this goes through a radical chain mechanism. And as we talked about in chapter 10, to produce peroxides, same mechanism. It's because a benzyl radical is particularly stable, so we can do that. At that point, we break the peroxide and then protonate the oxide, and we have the phenol, and or also get acetone as a byproduct. You don't need to know any mechanism or anything. This is just the way we get phenol, and phenol is very, very useful. It goes on, as you saw, there in many biological molecules and in many pharmaceuticals, drugs. There are phenol groups, and this is the way we get a phenol group if we need it. This is the way we get phenol, and then we can use phenol to make other things. We also saw that a lot of our in the radical chapter, we saw a lot of our food preservatives, such as BHT, which we put in as an antioxidant in our oils and peanut butter and stuff, also have phenol groups. Now, to review a previous reaction, you may recall that in a previous chapter we talked about the reaction of alcohols to produce an alkyl halide. We talked about this in chapter 7. So if you react an alcohol with a hydrohalide, the oxygen very negative, and remember this bond here between the hydrogen and the halogen is polar, and so the hydrogen is partially positive, and this is a strong acid too. So we have a proton transfer here basically. This grabs the proton off this very strong acid. These electrons are left behind on that bromide, which can very, very easily stabilize this. This was one way we were able to get hydroxide, which is a terrible leaving group, to be a decent leaving group. This will leave as water. This will only work if it's tertiary, because this would produce a tertiary carbocation, and then the bromide can attack as a nucleophile, and you get the alkyl halide. If you have a primary or secondary alcohol, the reaction will go a little bit different. Instead of going by this SN1 style mechanism, it will go by the SN2 style mechanism. Again, we protonate the alcohol with the strong acid, but then the bromide ion attacks in a backside attack simultaneously while the water leaves. And so either way, we get the alkyl halide from the alcohol. So if you react the alcohol with a hydrohalic acid, you can get the hydrohalide out. Now, an alternative here is if we want to make an alkyl chloride. So these were both bromides, right? The chlorides are a bit less reactive here, and so we're going to use zinc chloride here as an alternative. Here what happens is that the oxygen instead will react with the zinc here, and the zinc chloride as the positive part, and it will make this bond with the zinc here, which will make it a better leaving group, and then the chloride can then attack. And so it's just a different reagent here. If you want to chlorinate, if you want to change the alcohol to a alkyl chloride, you're going to need this additional reagent, the zinc chloride. So this is an old reaction as well. This was a variation on an old reaction. This is an old reaction we've seen before. Hydroxyl is a bad leaving group. We can make it a better leaving group by protonating it with an acid. Alternatively, we can react it with tosyl chloride and pyridine, and we can get a tosylate, which is a great leaving group. Remember here that when we do this reaction, the stereochemistry is preserved. So R/S is preserved. So that's something to keep in mind. Notice that it was on a wedge to start with. It's on a wedge to end with. At that point, we can get a SN2 nucleophilic attack from the halide. And at that point, you're going to get a stereochemical inversion, RS inversion. So the tosylate undergoes an SN2 reaction. You get a stereochemical inversion in the end. So the addition of the tosylate maintains the stereochemistry, but the nucleophilic attack by the halide inverts the stereochemistry. So old reaction, also from chapter 7. Now an alternative to this, kind of new alternative, reagents here. If you have primary or secondary alcohols, you can convert these to alkyl halides using, if you want to make it chlorine, you use SOCl2 with pyridine solvent. If you want to make it a bromide, you can use PBr3. So these are alternatives to the other reactions. A mechanism, here's a mechanism for you. So when it comes to the chlorination by the SOCl2, you've got, so this is SOCl2, the sulfur is double bonded to the oxygen. This is called sulfonyl chloride, by the way. That's a common name. And the two chlorine atoms. So here, this is a superpolar bond. So this oxygen, much more electronegative than the sulfur. So it's partially negative on the oxygen, partially positive on the sulfur, and it's even more positive because the chlorine is also electronegative. So everything's pulling the electrons away from this sulfur. So this sulfur has a super positive, partial positive charge. So that makes it a great electrophile. So the electrons here, they attack on the sulfur. And then after that, you have a loss of the chlorine here. So we have a same thing, attack, and then to avoid having five bonds on the sulfur, we use this resonance arrow to put the electrons on the oxygen. But then we have the loss of the chlorine as the leaving group. Chlorine, pretty good leaving. Chloride ion, pretty good leaving group. It stabilizes the negative charge quite well. This oxygen attached as a neutral nucleophile. So notice that this oxygen now has 3 bonds and 1 lone pair, so it has a positive formal charge to it. Now we use the pyridine here to deprotonate that alcohol. So it's a base, the nitrogen's a base here. Grabs the protons, leaves those electrons behind. Finally now, the chloride ions that came off here, they can attack. So we have a SN2 nucleophilic attack. And the oxygen and all the rest leaves here. And then we get SO2 gas, we get chloride ion, and then finally we have the substituted chlorine. So essentially this makes this reaction happen a little bit easier, a little bit faster, because what's really driving this reaction is that the oxygen is attacking this, these electrons are attacking this very, very positive sulfur here. A similar situation with the PBr3, phosphorus having a very low electronegativity, bromine having quite high electronegativity. So these electrons are being pulled all away from this phosphorus. So it's partially positive very much in here. So these electrons want to go and attack this. And then at that point, the bromide can attack, similar to the last reaction as a SN2, and we lose this. So essentially, these are other ways to convert the OH into a decent leaving group. In the case of the chlorine, we made it a good leaving group by attaching it to the sulfur atom here, and then having the whole thing leave as a big chunk. And same thing here. We made this a good leaving group by having the phosphorus, attack phosphorus here, the positive formal charge on the oxygen. Just like similar to if we protonated it, but it's a little bit more, this reaction is more spontaneous and more kinetically favored than the other. And then we have the backside attack, SN2 of the bromine. And so these are alternative reagents that, practically speaking, are easier to use than HBr for the bromination or HCl for the chlorination. Finally, in terms of elimination, in section 7, in chapter 7, we also talked about eliminations. We said if we use concentrated H2SO4 and heat, we can get an elimination on the alcohol. These follow an SN1 mechanism. We start by protonating the alcohol to make it a good leaving group, and then at that point, it leaves as water, and we have a carbocation, and then we can have a proton transfer, which will ultimately lead us to the alkene. Old reaction, same one from chapter 7. So like I said, in this chapter, we're seeing a lot of old reactions too, along with our new ones. Remember that eliminations will favor these acid catalyzed eliminations will favor the more substituted alkene. So you have to consider the regiochemistry. We're going to have mostly, almost completely, the more substituted alkene. So if we're doing an elimination here, we're going to eliminate right here instead of right here. So we get the more substituted alkene rather than the less substituted one. You would only get the less substituted one if we do E2 using a bulky base, such as potassium terbutoxide, TBUOK, as it's also called. So old reaction again from chapter 7, but it is involving alcohols, so it's worth mentioning here. If we want to do an E2, what we probably want to do is make the alcohol good leaving group first. So we'll react it with tosyl chloride, make it a tosylate, and then we can use a strong base and do an E2 reaction. Because remember here, the acid allows us to protonate the alcohol and make it into a good leaving group. But if we're reacting with a base, then we can't be the base is not going to protonate the alcohol. So instead, we convert it to a tosylate and then use the elimination. So yeah, the E2 reactions are generally synthetically, they're better too because they don't go through a carbocation intermediate, and so you're not going to get rearrangements, and you can control the regiochemistry depending on the base that you choose. If you choose a sterically hindered base, you can get the less substituted product. If you choose a non-sterically hindered base, you get the more substituted product. So now let's talk about the oxidation of alcohols. In fact, let me see here where I'm at. This card. Yeah, I think that's going to be it for this second video. When we come back next time, we'll talk about the oxidation of alcohols to produce carbonyls. So we've talked about the reduction so far of carbonyls to make alcohols. We use catalytic hydrogenation. So like just to recall, we H2 like platinum here or palladium. If we wanted to use a milder reducing agent, we could use the lithium aluminum hydride, Al. H4, or the sodium borohydride, followed by water, or some other protic, something that can provide the protons. This would be 1, 2, 1, 2. Next, we're going to talk about the opposite, so the oxidation of an alcohol to a carbonyl. And so that's where we'll start. That's where we'll finish off next time. I'll see you in the last lecture next time.